Access Control Lists, ACLs, also called Simply Access Lists, allow you to permit or deny packets for further processing based on packet information. They serve many purposes, for example, packet filtering and NAT. This lesson will address only router access lists and provide a foundation for in-depth learning about other types of access lists in the future. ACLs are a critical component in securing switches and routers. ACLs filter by address or subnet. Multiple Access Control List entries, ACEs for Access Control List entries, are possible within an ACL. Let us find out how to specify addresses in the next slide. ACLs use wildcard masks, like the inverse masks used for EIGRP and OSPF in the network command. To construct an inverse mask, the ones are swapped with the zeros in the binary representation of the subnet address. This is the same thing as taking 255.255.255.255 and subtracting the regular subnet mask. For example, 192.168.1.0/24 has a subnet mask of 255.255.255.0. Subtracting this mask from 255.255.255.255 yields 0.0.0.255 as the inverse mask. Keywords can be substituted for two special addresses. The word host is the same as wildcard mask 0.0.0.0, and the word any is the same as wildcard mask 255.255.255.255. For example, instead of 192.168.1.1, 0.0.0.0, enter host 192.168.1.1. Instead of 0.0.0.0.0, 0.0.0.0.0, enter any. Before configuring ACLs, let us discuss how they work in the next slide. First, create the commands to filter traffic based on address or subnet. Then apply the ACL to an interface. Place ACLs where they can reduce unnecessary traffic. Place extended ACLs as close as possible to the source address. This way, traffic is denied before it traverses many devices and uses up bandwidth, CPU processing, and device memory. For standard ACLs, placement should be as close to the destination as possible because they do not specify destination addresses. To apply the access list to an interface, use the IP access group command. Specify an ACL name or ACL number, and then in or out. The in option specifies an inbound ACL. This processes traffic entering the interface. The out option specifies an outbound ACL. The ACL processes traffic exiting the interface. The same ACL can be applied to multiple interfaces. That is why defining the ACL is separate from applying it to an interface. Processing varies upon whether the ACL is inbound or outbound. Let us discuss this concept in the following slide. Inbound ACLs process packets upon being received at the interface, immediately after the router checks the Layer 2 address. Denied traffic is not processed by the receiving router. Outbound ACLs process packets immediately before they are routed to the next device. Therefore, the router processes the packet before the ACL is checked. In the next slide, let us discuss packet processing of ACLs. Each packet received inbound or outbound on the interface is permitted or denied based on the ACL statements, the ACEs. Each ACE is processed in a sequence number order. If the ACL has no sequence numbers, the ACEs are processed in the order the ACEs were entered. Once the packet matches an ACE, the permit or deny is applied and the rest of the ACL is skipped. At the end of each access list, there is an implicit deny. This signifies that if a packet fails to match any specific ACEs, a deny will be applied to the packet. Let us discuss how ACLs are processed in the next slide. Router ACLs never apply to traffic from within the router. Suppose you have router R1. A ping, or even an extended ping using another R1 router interface, entered on R1 cannot be used to test an ACL on an R1 interface. Therefore, you must ping from a device on the other side of R1. Keep this in mind when you are testing ACLs. ACL logging can be enabled. This means that messages about matching packets will be generated. In this case, packets are normally process switched. This is much slower than the default packet forwarding method, Cisco Express Forwarding. Therefore, using logging slows packet processing considerably. Use the log parameter only when absolutely necessary. In the following slide, let us focus on planning ACLs. You have learned many rules concerning ACLs. These rules are complex. This means that you must plan ACLs carefully. Remember how many ACLs can be applied on an interface by the 3 Ps. 1 ACL per protocol, per direction, and per interface. Enter ACEs in a deliberate order. A more specific ACE should come before a less specific ACE. For example, an ACE with a /24 subnet should be configured before one with a /8 subnet, all other considerations being equal. Enter ACEs in order from more to less frequently occurring conditions. If an interface receives a large amount of traffic from one subnet, specify that subnet before you configure others. An ACL has an implicit deny statement at the end. Therefore, an ACL should have at least one permit statement in it. Otherwise, it blocks all traffic. Once the ACL is configured, determine whether it should be applied on an interface using either the in or the out parameter. Using a text editor is recommended because the ACL commands are long and they are difficult to back out. In the next slide, let us focus on standard access lists. A standard access list specifies conditions for permitting or denying a packet based on the packet's source IP address. There are 2 types: numbered and named. Standard numbered access lists use numbers 1 through 99, or expanded numbers 1300 through 1999. This provides a total of 798 numbers available. Configure access list number, deny or permit, source IP and source wildcard with optional log parameter. To configure standard named access lists, configure IP access list name standard, sequence number, deny or permit, and the rest as in standard numbered ACL. An ACL name is case sensitive and must begin with an alphabetic character. No punctuation or spaces are permitted. Statements automatically increments by 10 when sequence numbers are omitted. Take some time to review the command syntax on this slide. Let us discuss extended access control lists, which have many more options than standard ACLs, in the next slide. An extended access list specifies conditions for permitting or denying a packet based on Layer 3 and 4 packet information such as IP addresses, Layer 3 protocol type, Layer 4 port number, type of service (TOS), IP precedence, and or all TCP flows except the first using the established parameter. Choose the appropriate Layer 4 protocol after the permit or deny statement. For example, to filter FTP or Telnet, use TCP. To filter TFTP instead, use UDP. For protocols that can use both TCP and UDP, enter 2 separate ACEs. There are 2 types of extended access lists, numbered and named. The same 2 types are available in standard ACLs. Extended numbered ACLs use numbers 100 through 199, or expanded numbers 2000 through 2699. Let us continue our discussion on extended access control lists in the next slide. Take some time to look at the syntax for both extended numbered access lists and extended named access lists. Let us look at one of the options for an extended access list, the established parameter. The established parameter applies only to TCP since this protocol is connection-oriented. It keeps track of the flow of packets in a conversation. UDP is connectionless, so established, cannot be used. Let us configure an access list which allows hosts in 25.25.11.0/24 to access 25.25.34.0/24 and permits return traffic. Hosts on 25.25.34.0/24 cannot initiate traffic to 25.25.11.0/24, but it can return traffic from 25.25.11.0/24 subnet. Take some time to review the command. In the next slide, let us understand how to delete ACL. Before deleting an ACL, you must remove the application of the ACL on an interface by prefacing the access group command by no. To delete a numbered ACL, delete every line of the ACL. This is done by prefacing each with no. To delete a named ACL, delete the name. Take some time to review the commands. Let us discuss how to edit ACLs in the following slide. Named access lists can be easily modified, but numbered ACLs cannot be modified depending on the iOS version. This means that each ACE in the numbered ACL should be deleted and then re-entered. This involves the same procedures as discussed in the previous slide. To verify that an ACL has been modified or removed, use the show run command. Let us discuss this command in the next slide. Use show run command to verify ACLs and the interfaces they are applied to. If your iOS version allows it, you can use a pipe only to list the running configuration starting with the first occurrence of the string access. Take some time to review the command and the output. In the next slide, let us focus on VTY Line Security. An access list can be used to secure VTY lines. You can limit access on the VTY lines to a management device address. Then only the network administrator has VTY access to the device. To limit Telnet or SSH, the ACL is applied with the access class command. To limit Hypertext Transfer Protocol HTTP traffic, the ACL is applied with the command on the slide. A standard numbered or named ACL can be used. Take some time to review the configuration. In the next slide, let us discuss how ACLs can be used for security. ACLs can also be used to filter traffic passing between trusted and untrusted networks. A trusted network is one that you have administrative control over and you trust that its traffic is relatively safe. According to Cisco, an untrusted network is not trusted. A firewall device or firewall software is often used to separate a trusted network from an untrusted network. In addition, there is normally a demilitarized zone, DMZ. Trusted and untrusted entities have access to this DMZ. Web servers such as HTTP and mail servers are located here. The figure shows how the firewall can control the traffic moving between the LAN, the DMZ, and the Internet. The LAN is the trusted network, and the Internet and DMZ are untrusted networks. Now let us look at some commands and ACLs that can help secure your network. Implementing ACLs for security is a balancing act between providing access to the LAN and protecting it from harm. Unneeded services can be a security risk. It is better to disable them if they are not needed. By default, in Cisco iOS versions 11.3 and later, most TCP and UDP servers for management are disabled. For an earlier iOS version, disable these servers in configuration mode with the commands on the slide. Let us discuss Cisco Discovery Protocol in the next slide. Cisco Discovery Protocol, CDP, is helpful in troubleshooting because it provides information about connected devices. If an attacker gains access to the network, CDP could be used to discover a large amount of information about your network. As a result, CDP is normally disabled. However, if Voice over IP (VoIP) is being used, CDP must be enabled. Take some time to review the commands to disable CDP. Let us move on to the quiz questions to check your understanding of the topics covered in this lesson.